Hello and welcome back to Proximity Math. Today I'm going to go over the 2007 Aime Ii number 15. This is number 15. So, where should we look? Okay. For a circle, omega A, omega B, and omega C with the same radius are drawn in the interior of ABC, such that omega A is tangent to sides AB and AB. AB and AC, so it's near A. Omega B is near vertex B and tangent. Omega C is near vertex C and tangent to the triangle. And omega itself is externally tangent to all these three circles. Okay, the same radius, so these are congruent circles. And the sides are 13, 14, 15, which I drew right here. So it's asking us for the radius of omega. Not circle, okay. So if you let these circles over here, actually, if you've noticed, we've not been given which sides are which, because it actually doesn't matter which we choose to be. So we can choose this to be A, for example, B, and C. And we don't need to label the circles to find out, label the circles by their respective names, because they're all the same. And we're asking for their common radius of colors. So we just make them tangents so we can get an accurate diagram. This is omega in the middle. So first of all, let's connect their centers, because they'll give us the sum of the radii of the two tangent circles. Because they're tangent. That's something you would do right off the bat. Okay. And if you let the middle circle have a center of O, because these three are congruent, which means if you drew a triangle with the centers of omega A, B, and C, then voila, it's a circumcenter. O is a circumcenter because it's equidistant from the vertices. You can draw a circle with radius 2r. Anyway, since O is circumcenter, it's equidistant from the three centers. We can use that fact to somehow lead. Next, let's use the fact that each of these circles are tangent to the triangle. So if I drew let's say this, and since they're tangent, the triangle it it forms a right angle. It's perpendicular to the radius. Okay. So what can we do with these? Well, if we split this along like this, then these two right triangles are obviously congruent. These two are, and these two are. So I put 14 as the base for a reason, because since it's 13, 14, 15 right triangle, you can actually drop altitude from A to make this, if you split it like this, you have a 5, 12, 13 triangle on the right triangle on the left side, and then 9, 12, 15, which is a 3, 4, 5 right triangle on the right side. Okay. So maybe you can do that fact too. But anyway, you can also use the fact that these triangles are congruent, and notice that now we have the angle bisectors because these angles of the congruent triangles are also congruent. So if we extend C through here, let me make this blue so you can see through it. Okay, and these angle bisectors intersect at a point which is in center of the bigger triangle ABC. And let me actually label the smaller triangle with circumcenter recon XYZ. Okay, so now, uh, well, what can we do? Actually, if you look closer, we have a lot of right angles. So, like here, for example, right angle, and these are both our radius of the common radius we're trying to find. Meaning this segment is congruent to this segment and also parallel to it. And the same goes with these. So all XY is parallel to AB. Okay, that means we must have, and this would be a key observation, that XYZ is similar to triangle APC. Okay, so since it's similar, we can find some ratio of similarity maybe and then equate it. Okay, if we have the circumcenter and a ratio, then we can find 2R and therefore the radius. So there's a formula we can use. Actually, we can swap them out. This form would be helpful. So this will give us the formula would give us the circumcenter of circumradius of the bigger triangle ABC. And we have we can also use the fact that I split it like this. The altitude is of length 12 and the base is length 14. So we would have the area being 1/2 of 12 times 14, which is 84. Right? And use cancel now and find that. Wait, actually, um, okay. Oh yeah, that's what I did wrong. This is 6 times 14. So I have 65. 65 to 8. That's the radius, circumradius of the bigger triangle. And the circumradius of the smaller triangle is 1. So the radius, circumradius of the small triangle to the bigger triangle. If you find another ratio, then you can solve the problem. So use these congruent sides, we get well, if we had them. So how would we get them? Well, since these are right angles, and you have the interior of the big triangle somewhere here, what if we take the in radius of the big triangle? The in radius. Yeah. What would the in radius be? Well, it would actually be the in radius of the, if you look closely, since this is a right angle and the in circle of the inner triangle is the right angle, then these lengths add up. Meaning the in radius, well, let's call it x, the in radius x of the inner triangle, xyz. We have the radius r as the height here, right? So the in radius of ABC, the bigger triangle, would just be r plus x because we're adding these um, segments which are both perpendicular or parallel to each other and perpendicular to the base. So the smaller triangle to the bigger triangle is circumcenter ratio, and then the incenter ratio would be x over r plus x. Okay, and um, well, we don't know the in radius of the smaller triangle. So instead, let's try something similar. What if you take, okay, what if you let all of this be x? Because we can find that we have information of the bigger triangle. Okay, so then instead it would be x minus r over r. Okay. And what is x? The total and radius of the bigger triangle. So we can use the areas RS, which we found is 1/2 times 14 times 12 is 80. And the semi-perimeter is 13 to 15 over 2, which is 21. So um, we would get uh, R is divided by 21 4, and sorry, not R, it's X. This is the in radius. Make sure you don't make a mistake. You want the in radius of the bigger triangle, which we labeled as X. We're using really risky variables here, but now that we have it, we have only R here, which is a very good thing because now we can really just solve for R. Okay, cross multiply or however you want. Do the algebra. Get cross multiply these 65. Have 65 times 4, 65 eighths times 4 minus 65 eighths are make sure you don't make a single mistake here because you're on the final steps. And I literally just did 5 eighths are okay. 2 r squared. Okay, now that we have that, you can multiply everything by 8 r squared minus 5 r minus 260 equals 0. And you can, I guess, factor it. Or, 2r over 65 radius of the circumradii, and then the inner radius. Okay, I see what I did wrong. I think the inner radius is just, yeah, that's what I did wrong. This is going to be x as the inner radius of this, and then what we actually got to before just now, and this would be minus r. Okay, and so the variables again. So 8r cross multiplying equals 5. And then we would get 64. And this is actually being another mistake. I see. So actually have the page here. It should be like a regular pencil stay and cross of the column. And this is 3 times 43, so it's relatively prime to 55, which is 5 times 13. Finally, finally, we have done the theme number 15. Find m plus n, where it's the numerator and the denominator. So just sum these, and don't make a mistake. 389. All right. Thanks for watching, and I hope this helped you. We use similarity slash velocity in this problem, and this should help you a little get better.